Today we are having the second lecture of this lecture series on structural design of cost-effective, lightweight, hybrid, multi-story buildings using Eurocode. And the today's topic is a structural design of reinforced concrete members subjected to flexure using Eurocodes. So I would like to welcome you all and our resource person, Professor Tisan Jayasinghe. Professor has been with us for the last 2 years, conducting these knowledge sharing sessions. And Professor has done many studies on these cost-effective structures and housing construction. And recently, Professor had a model building at the Exmo exhibition at University of Moratua, which was a key highlight of the exhibition. And we are so grateful him for sharing his knowledge and expertise on the field with us throughout this lecture series. And over to you, sir.
Okay, thank you, Bandhuka. Now, last time we talked about the fundamentals, the loads, all pertaining to Eurocode while comparing those with British code. Now, toward the latter part, I was talking about the use of concrete, how to make concrete and how to find the mixers, how to control the delayed Ettringite formation. There are so many things. And delayed Ettringite formation was first detected in Southern Highway. So that's also an interesting story. So I thought I should tell a little bit about it because such historical events are very useful for the practicing engineers today because you may not know the real story, but as a person who had nothing to do with Southern Highway when it was started in 2003, but had huge amount of things to do after 2009, end of 2009. I can tell few interesting stories that would be very useful for young engineers. How to practice engineering, because when you first thing is you will get a lot of knowledge from the lecture series, but at the same time it's very useful how you should practice when you are a consultant. That is also an important part of knowledge sharing. So I thought I should say a little bit, but before that, because last time towards the end of the lecture, we rushed a little bit. So I thought I should, repeat the last part of the lecture in little more detail before we go into the design of concrete elements. Is that okay, Bandhuka?
Yes, sir. Fine.
Right. Okay. So I will start with the DF story. So that is, how to make a mixed design. So let's say we want, when we are using Eurocode, we have C2530. C25 is cube cylinder strength. Third is cube strength. We also have C3037, and we have many others. And last time I showed you the type of things we have, and I can share the screen. And if I go down on this note, I can clearly show you. I mean, you might see some of the things that you have already seen last time, understood. But this is the important chart. It says one is cube strength, the other one is cylinder strength. So I will enlarge this little more so that you can see it clearly. 150, 200%. Yes. Now you can clearly see that we have cube strength 30 and the corresponding cylinder strength is 25. We have 3730, 40, 3545, 4050. And then here we have 2025, 2530, 3037, 3545, 4050, 5060, and so on. But there's a upper ceiling and 4555, 5060. So those are the values you can see. And these are the mean strength values, mean values. And then you get tensile strength values, which are useful for pre-stressed concrete design, but not generally for this. But again, the most important other parameter is the elastic modulus. You can see lowest quality concrete has only about 25, 26, 27, whereas high strength concrete has not extremely high strong concrete, but high strength concrete has something like 37, whereas extremely strong concrete like 105 megapascal would have about 42. So that means nearly 50% increase in the stiffness of the structure, purely because of the rise in elastic modulus. And that is the key reason for people, many modern designers, to like reinforced concrete for tall buildings. Because with the technology we have, we can now go for high strength concrete. So let's see how to go for high strength concrete as well. So let's start with C30. Sorry, 30 megapascal cube strength concrete. So I told you, in concrete we get cement, sand, aggregate, water, and wet density. So I also used, like all of you, I also used DOE method, and we used to get a lot of this one. Stop sharing. Right. So in concrete we get cement, sand, aggregate, water, and wet density. I also used a lot of this DOE method when we got consultancy work from various organizations asking us to recommend a proper mix. So when I was looking at these specifications and the requirements, I found some interesting relationships. So today is 6th December 2023, Civil Engineering Sectional Committee, lecture number 1, page number 1, lecture 2. Lecture 2. Right. So I found some interesting parameters. They are these: 2500. Water requirement is 200. I did not have any other parameter, but I also had, if this is x, this is y, I knew x or y of x should have a minimum value of 1.5 and a maximum value of about 1.8. So I knew about that relationship as well. So what I didn't know was cement, and when I was doing designs, I found that cement content is, ours is 30 multiplied by 10 plus 50 works. So cement content of our 350 can easily give 30 megapascal concrete. So that's something I found. Then when I looked at all these numbers, I thought, okay, now this is something special. That means, you know, x plus y is equal to x plus 1.5 times x. This is 2.5 times x. So x plus y is equal to 2500 minus 200 minus 350, and that gives 1950, and x is equal to 1950 divided by 2.5, and that gives, what is the value that you get for this? Today I'll find it. What is the answer? That is 1950. 1950 divided by 2.5. The answer is 780, which means y is equal to, multiplied by 1.5, 1170. So I found that, you know, mixed design is something that we need not waste time. You just use this method and you get 780 as answer and 1170. Pretty straightforward. And you get a mix that might work in few seconds. And as an engineer, I felt, okay, now that's a wonderful method. So I kept on using this. So one day, Professor Sujiva Levangamagi asked me, there's a company needing 65 megapascal in 24 hours using steam curing for manufacturing round pots. So that particular company wanted 65 megapascal in 24 hours using steam curing for manufacturing round pots. So he asked me, okay, what is your solution for that? Then I said, okay, let's look at it this way. We want cement, sand, aggregate, fly ash, water, wet density. That company was keen to use about 15% fly ash as well. That was a great relief because you had to control the temperature of the manufacturing process to prevent DEF. So I started plugging in numbers. So this is the time that it took. Okay, I said okay 2180 because I'm going to use some fly ash because fly ash has a lesser density than cement particles. And so I'd like something like 600 cementitious material. So I said, okay, 500 cement, 90 fly ash or 100 fly ash, just above that. Because when it says 15%, you need not be exactly 15%. And X, Y, because this has to be compacted properly, we are going to use a graded mix of 10 millimeter and 20 millimeter and sand. But for this calculation, this is Y, and we are going to use a mix of 10 millimeter and 20 millimeter aggregates because they are smaller poles. You don't have very large space, but I didn't want to eliminate 20 millimeter either. And I said I'm going to use 125 kilograms of water by using a very high quality admixture. We call it high grade super plasticizers. We call them high grade super plasticizers. High grade super plasticizers. So, for example, I mean, if you are looking for one such very high quality at affordable prices, you can actually contact one of the leading admixture manufacturers in Sri Lanka, and his name is Ravi Nisanka. He has a great knowledge on admixture manufacturing. So if you want, I can ask him to do one lecture as well on this series. And his knowledge is excellent, and he knows he himself manufactures Note 712481. So we went for very high quality admixture. That allowed us to go for 125 as water. Now you have to ask why. On what basis I am making these decisions? I need very high strength with steam curing. So I'm aiming for something like 65 megapascal in 28 days that I achieve it by using steam curing in 24 hours. So it's good to have something like 600 cementitious material, not cement, but cementitious material. And because these are very small poles like this, hollow poles, and on this side it may be about 170 millimeters. Here it may be about 220 millimeters, very small. So you don't have to worry about DEA due to high cement content, but you have to, when you are doing the steam curing, you have to control the temperature. Now let's look at what I did. I said, okay, so I'm going to use 1.5 ratio. Why? Because I need to compact it properly. To compact it properly in a small section, it's good to have a lot of sand rather than having a lot of aggregate. So I said, okay, I'm going for 1.5 ratio. So if you look at the numbers, x plus y became 2480. 2480, 2480 minus 125 minus 600. 1755 divided by 2.5 gives 702 here. Multiplied by 1.5 gives 1053. And you can add up all these numbers and see that it is 600 plus 702 plus 1053 plus 2480. Sorry, not 2480. Is 2455. So have I got something wrong? So the answer is 2480 minus 125 minus 600. The answer is 1755 divided by 2.5. Divided by 2.5. Answer is 702 multiplied by 1.5. 1053. So the equation is 600 plus 702 plus 1053 plus 125. It comes to 2480. So I got these numbers, and so you can see 65 megapascal in 24 hours. Extreme case, even with steam curing. So we tried this mix. Next day, after 2 days, Professor Sujiv Levankamaki came and told me, oh, it has worked. The mix that you gave in few seconds has worked. So now we have to see what is the logic I have used to come from 30 megapascal to 65 megapascal in 28 days. So 65 megapascal in 24 hours using steam curing is equivalent to 65 megapascal in 28 days. Is that clear, Banuka? Banuka, is that clear? Anybody else who can answer? Please give a comment. I like to see.
He's having a technical issue, sir. I am Bashit. It's clear, sir.
It's clear. Right. Who is having a technical issue?
I'm Bashit, sir.
You are Bashit. Yeah, right. Okay. No technical issue now. It's working.
No, sir. Actually, Banduka is having technical issue. I'm Bashit, sir. Bashit.
You are Bashit. Right. Okay, Bashit. Not Banduka. Right. Okay. Right. So Bashit is the civil engineering. Banduka is civil engineering sectional committee coordinator for this course and or series of lectures, and Bashita is one of the best representative of our MSc program. So both are familiar with the system, and so thank you, Bashita, for answering. Okay, so I like that little feedback because this is something that we have to make sure everybody understands. So you can see I have jumped from 30 megapascal. I'll say this is equivalent to 65 megapascal in 28 days. Now we have to see how I jump from 30 to 60. Let's say 65. We forget about 65. We say 60. Right? 30 to 60. How did I jump? What is the method? What is the thinking process? So I'm going to explain the thinking process. For that, I'm going to use now 40 megapascal, 30 megapascal with super plus size. So we have cement, sand, aggregate, water, and wet density. Is that clear? I'm going to explain this thinking process so that you yourself can easily master it. Is that okay, Bashit?
Yes, sir. It's okay.
Yeah. So cement. Now I'm going to use an admixture. So the first thing you enter is admixture. 160. It's a super plus size. Like Supercrete, created by Millennium Technologies. That's a name, trade name. And so density, as long as I don't use fly ash, density is 2005. As long as I don't use fly ash, density is 2500. X and Y will all depend on whether I'm going to pump or drop. So I can use a bottom opening skip and drop it, like in a large pile cap. If I'm dropping, what happens? I can say Y over X is 1.7 to 1.8. If I am pumping, X, Y over X is 1.5 to 1.6. 65. I'll say 1.65 to 1.8. So this is dropping. 1.65 to 1.8 is dropping. 1.5 to 1.65 is pumping. Right? And now I know concrete has a friend. It has an enemy. Who is the enemy? Water. Who is the friend? Cement. Cement is the friend, enemy is water. Now I have reduced the enemy. So what can I do for the friend? I can reduce the friend as well. 320. So the equation is 30 multiplied by 10 plus 50 minus 30. So I reduce the cement by about 30. Can you see how I'm manipulating? This is page number 3. Today is 6th, 12th, 2023. So now I can again plug in the numbers, and I'm using a Y over X of 1.5 because I'm pumping. You can even use 1.55 or 1.6. Generally, I don't go up to 1.65, but it's a good margin to look for. So then I will say 2,500 minus 320 minus 160. 2,500 minus 320 minus 160. 2020 divided by 2.5. I get 808 here. Multiplied by 1.5. I get 1212. So that is the mix. Can you see how we logically change the parameters? Bashita?
Yes,
is it
sir.
clear?
Yes, sir. Clear,
Very
sir.
logical process. Very logical process. Right? Very logical. With a very logical process, we are changing the parameters. Got it?
Correct.
Now you might say, okay, now I like some fly ash in it. I like 15% fly ash. What is the reason? You are doing a large concrete pour, and you have looked at. So this is the paper on DEF. Now you are familiar with this paper. And in this paper, I have shown you that there's one very important chart, and that is this chart. How the peak temperature varies. Now you can see. Now let's say you are having something like 3 meter thick concrete to be done, a very large pile raft. Generally, pile rafts are not applicable to Sri Lanka, but let's assume that the engineer has now designed a pile raft, 3 meter thick raft on the piles. So it's 3 meters thick. So what is the maximum cement content you can use? 275. Anything above, you can see temperature goes above 70, and you are not in a position to make the concrete really cool during the, because it's a very long concrete. So even if you start midnight, you might have to finish it doing it throughout the day, following day. So you have no control over the temperature. So you have decided, okay, the maximum I can use is 30. The placing temperature has to be 30, but the maximum temperature is 70. So this shows you, okay, now you can't take a risk. Why? Because if you use more cement, you might get delayed laterite formation, because these are maximum. So as a design engineer, now you have to take a decision. You have decided to use grade 30 concrete, 30 megapascal cube strength concrete, and the maximum cement you can use is 270. So anything above, you are going to get a temperature above 70. Can you understand that, Bashita?
Yes, understood.
Yeah, okay. So now I need 30 megapascal concrete, but the problem is our structure. But just one moment, I'll show you the repercussions of not doing it wrong. What are the repercussions of doing it wrong? Can you see? Do you like to have the pile cap after 3-4 years after construction like this? Bashita?
Yes, sir.
You like or don't like? Do you like to have this pile cap like this, cracked like this after 3-4 years? I'm sure the answer is no. You don't like it, huh? Right.
Yeah.
Okay. So you don't like it. Now you want to make sure it doesn't happen. So what is the way you make sure it doesn't happen? You need 275 here. But if you want to go for fly ash, use 50 kilograms of fly. Now the moment you use this, I'm modifying so that you can see what is going on. What will happen to this? This side will become 2480. And still the client says, okay, we are going for 30 megapascal. I don't want to use a hypergrade super plasticizer. I'm going with the normal plasticizer, super plasticizer. So it's 160 remains there. Now we have to look at the numbers again. So what are the numbers? $2,480 minus 325. So you can see the addition of 275 and 50 is 375 minus 160. 1995 divided by, now you want to make sure the mix is strong. So you have decided, because this is a drop type thing, you have decided y over x is 1.65, because you are not going to pump a lot, you are going to drop a lot. Let's assume you are going to drop a lot. Then this number should be divided by 2.65. So you get 752 multiplied by 1.65, 1242. So you can see the numbers are 2480, 160 water, 1242, little more aggregates, less sand. What is the main difference? 275 cement, 50 fly ash. What is the maximum temperature that this will reach? The maximum temperature of this mix will be 70 or below 70. Can you see how to think about optimizing the mixers? Mashita, is that clear?
Yes, sir. Clear.
So you came up. So as a structural engineer, now you have to do this 3 meter thick raft. You are the structural engineer. You are designing it. What will you select? 30 megapascal or 40 megapascal? What will you select? 30 or 40? You have the option of selecting 40 as well. What do you select 40? What are you going to select? 30 or 40? What are you going to select? 30 or 40? What are you going to select? 30 or 40? I'm asking a question. Can somebody answer? But I need a logical answer. You have to tell me why you select 30 or why you select 40 or why you don't care about 30 or 40. First is you select 30. That is A. Who wants A? On the chat you can indicate who, if you are agreeing with A. Who wants B? 40 megapascal. Number C, the third choice is I don't care whether it's 30 or 40. What is the correct answer? Correct answer is 30. Why? You know, now if you are having a 3 meter thick concrete, are you going to rely on the flexural action or strut and tie action? You know, when you are designing a pile cap, what is the method you use? Not flexure. You are using the strut and tie model. So when you are using a strut and tie model, there's huge amount of concrete to be a strut. So do you want it to be 40 megapascal? No. I mean, if you are using if you are designing a 30 megapascal or 40 megapascal is important only when you are designing as a beam. Even as a beam, you have a 3 meter thick raft. Would it matter? No, it won't. Whether you use 30 megapascal or 40 megapascal, the amount of reinforcement that you need will be exactly the same. So in such a scenario, is there any point in selecting 40 megapascal? No point. So don't select high strength concrete for the sake of selecting a high strength concrete. How are you going to manage it? Very simple. What you do is, you have a thick raft, 3 meters thick. So on one hand, you can push to the limit and specify 35 millimeter cover. On the other hand, you specify 45 millimeter cover. What is the impact on? So this lever arm, so here the neutral depth of the neutral axis is about 100 millimeters. The reinforcement is here or here. Would it make any difference? No. The same reinforcement, but what is the durability of this one? Much higher. Much higher. Durability of 45 or 50 millimeters will be much higher. So what you do is, you don't increase the grade, cube, strength based on durability constraints. You keep it as low as possible, but you will increase the cover, because for thick sections, cover has no bearing on the steel ratio. Have you got that point?
Yes, sir.
Very clear?
Yes, sir. Clear.
I got it. Now let's say in the same building you are doing some columns, and some of these columns are going to be supported on 30 megapascal transfer plate. So these are, or a raft. Say, so these are raft foundation. So on the raft foundation, we have some columns, and you found that the architect doesn't like two big columns, so you have decided 40 megapascal. And this is 30 megapascal. Is it allowed? Suppose having 40 megapascal supported on 30 megapascal. Yes, as long as the difference is less than 10 megapascal, it's okay, no need to worry. But here you look at it in a different way. Now what I say, 30 megapascal in how many days? 28 days. And it has 15% fly ash. So when you have 15% fly ash, what is the curve? It is going to go like that. So after about 1 year, you might say now the raft foundation has 40 megapascal. That's why we went for the trick. We added 15% fly ash. Now what happens? The curve goes like that. On the other hand, I made a mix without fly ash. Here you can see 320 mix. What is the path it takes? It will go like this. So you might have temperature problems, but it might go very flat. So this is 320 cement concrete. This is 275 plus 50 concrete. Which one is better? The fly ash base, 15% fly ash base concrete is far better than Portland cement on this concrete. Is that clear? Is that clear?
Yes.
Bashidu? And others also can tell if they are not, if anything is not clear, tell me, I can repeat it. So there are two options that you have to think as a structural engineer. One is the cover. Cover is very important. I told you why cover is so important last time. By looking at, how the pores are filled up with calcium hydroxide and how the fly ash can react with calcium hydroxide and fill up the pores with a stronger material, and with the fill up of pores created by the evaporation of excess water, you are creating a crust which is very strong. You are creating a cover zone which is very dense, and when the cover zone is very dense, the pores are not connected, so you'll find the ingress of carbon dioxide into the concrete with the reaction that we call carbonation is very, very slow, very, very slow. Even after 100 years, you might still find the concrete is super strong and not affected at all because the carbonation depths are very small. So that's why the curing of concrete is extremely important. Okay, now you can see when you use fly ash based concrete, it's good to continue the reaction, continue the curing at least for 14 days, so that over the 14 days, all tricalcium silicate will react, form a lot of calcium hydroxide and calcium silicates, and calcium silicate gel, create a strong concrete. Now, fly ash can come into the action and continue to react with calcium hydroxide generated by the reaction, and then create a very dense concrete and a very strong concrete, and you target 30 megapascal in 28 days. But over 1 or 2 years, you will find now you are having, after about 1 year, you will find, if you take a core and test it, you will find the concrete in the raft is 40 or 45 megapascal and continuing to increase the strength. So will they be, by that time you will find now it's a 50-story building, 30 floors have been completed, and by the time second year goes, all the floors are completed. By the time the maximum dead load comes on, the raft is not a 30 megapascal raft, though you design it as a 30 megapascal in 28 days. Now it has, now 2 years have gone, you have cured it properly, you had fly ash to continue the reaction. Now it's, you take a core and see, you will see the real concrete can be ranked as 45 megapascal cube strength concrete. So that's how the engineers should think. They should not be confined to codes and think as for a cookbook pattern thing. So you would have seen some ladies when they don't know how to make a food item, they look at a cookbook, a cookery book, and they copy all the details to the letter with the hope that they will make a delicious food item. Now, engineers should not be doing that type of things. Engineers should have brains to deviate and make better products at a cheaper cost. So if you are making this concrete at site, what is the cost? So we look at the cost of these two concretes. That will give you a good insight into 320, 808, 1212, 160. Or those numbers are not necessary. The other one is 275 plus 50, 752, and 1242. The price of, what is the price of 1 kilogram of sand? 550. What is the price of 1 kilogram of coarse aggregate? Now we are using half-inch aggregate and 3/4 together. So if you are using, say, when you want 1242, you might use say 400 of 600 of half and 642 of 3/4. So aggregate half-inch is 550. That's a 250. 1 kilogram of coarse aggregate, 3/4 inch. What is the price? 225. And then sand, all are available. Now I'm going to find the cost. Right? Find the cost, and for that I'll use these values and the mixers. And aggregate cost will be pretty similar because the cementitious material quantity is the same. So per meter cube, the cost will be 320 multiplied by 40. 1 kilogram of cement is 40 rupees. So you get 320 multiplied by 40. 12,800. Now you can see why concrete is so expensive these days. 32,000 rupees, 2,000 rupees per meter cube. Supply to the yard or supply to the site. 808 multiplied by 250. Say 225. 225 is 1818. Oh no, I got it wrong. This multiplied by 550. 808 is sand multiplied by 550, and that is 4,444. And 1212 has to be multiplied by 225. 2727. Now you can see the addition. Admixture cost will be 3.25 into 600. Admixture cost is 1950. It's a constant for both. So the answer is 12,800 plus 4444 plus 2727 plus 1950. 12,800 plus 4444 plus 2727 plus 1950. 21,000, 22,000. Approximately 22,000. Now we look at the other one. 275 fly ash. 1 kilogram is 15 rupees. So 275 multiplied by 40, 11,000 plus 50 multiplied by 15, 750 plus 752 multiplied by 550. 4136 plus 600 of 200, 600 of 250, because half inch aggregates are a little more expensive. 1500 plus 640 of 2.25, 1440 plus 1950. 11,000 plus 750 plus 4136 plus 1500 plus 1440 plus 1950. 21,000. So the second one is 21,000. 1,000 rupee saving per meter cube. You have a large pore. 30 meters by 40 meters by 3 meters. So how many meter cubes? 30 multiplied by 40 multiplied by 3, 3,600 meter cubes multiplied by 1,000 rupees saving multiplied by 1,000, 3,600,000. By doing anything? No, doing nothing. Just by getting the mix right, you save 3.6 million on the foundation. And that's how you show your colors. So you look at this and then, but this is not the real saving. To supply 1 meter cube to the site, it can vary between 26,000 to 32,000, depending on the type of mix. So let's say it costs 28,000, because they are buying a lot. The suppliers have decided to supply us 26,000. What is the reason for this to become 26,000? Bashita, can you tell me what is the reason? Why the side mix costs 22,000, whereas the mix from vacuum plant is going to cost you 26,000? Tell me the reason. Anybody in the audience? Can you tell the reason?
Transport cost.
So yes, transport cost. Yes, transport cost and also the profit of the vacuum plant. So there are many things that we have to look for. So if you can see, if you are having a massive hole, sometimes installing a small vacuum plant at the site may be cheaper. Having a small vacuum plant at the site will be cheaper. But then you might say, oh, it's not sophisticated. But I can tell you the story of Veragala project, which was constructed by a civil engineer called Guna Dasa, who graduated from University of Monaco in 1993. And do you know what is the maximum capacity of a concrete mixer that was available for this 2,200 million project? It was half a bag capacity concrete mixer, and this engineer made it happen. So you have to say, and if you look at Chinese contractors, sometimes they come with very old machinery but get the job done. So what you have to say is, don't say these are not practical. These are very practical. And if you want to make a huge saving, let's say you get the concrete mixed at site at 21,000 against 26,000, 5,000 rupees saving per meter cube, and 3,600. It might take few days to complete the job. Doesn't matter, because you are never going to get the DEF. So you are not in a hurry. You can concrete for 5 days and finish the job. Multiplied by 5,000. How much saving you are going to get? 18 million. Now, this is the way that you have to look at construction if you ever want to get the construction of Sri Lanka back on track, because the costs are too high today, because the transportation costs are exorbitant. So you have to do something about it. And the only way you can solve this problem is looking for how to save even a cent from every item. And that's why the good knowledge of concrete technology is so important. That's clear? Is it clear?
Yes, sir.
Right. So you are happy that you have to do something. And as engineers, we can do it, provided we have this knowledge. Because we can do trials. So how are we going to do trials and get confidence? So what you do is you cast about 100 cubes from one mix. And then you are going to chase at 2 days, 3 days, 5 days, 7 days, 14 days, 21 days, 28 days, 45 days, 1 month, 2 months, 3 months, 4 months, 6 months, 1 year, 2 years, and so on. Then you put it on a log scale here. Get a curve, and that is the strength development curve. So the moment you generate few strength development curves, you will get huge confidence, and you will be able to start doing adventurous things with concrete. As I do often. I do these calculations and I do risky things, knowing very well there's no risk. Why? I have understood the fundamental way how the concrete works. So you create a strength development curve like this, and then test them, and then generate the curves. And that's how you develop your own skills. And these type of skills will be with your company who has sponsored the work, so that you can make, when you are tendering and you are doing the tendering, you can actually quote knowing how you are going to do it at a lesser rate. But at the same time, consultants also should be willing to take risks. Sometimes some consultants are too conservative and they say, oh, I don't accept anything other than a mix from a truck mixer. So you have to deal with that type of consultants as well. But generally you have to be adventurous if you ever want to come out of the mess that we are in. Now 40 megapascal concrete. For what? For the column. Because I said in this big, large, tall building, 50 stories, I need 40 megapascal concrete for the column at the first 10 floors. In the first 10 floors. So how to get 40 megapascal? Cement, sand, aggregate, water, and wet density. So I need, so wet density, I'm going to use 15% fly ash. Why? Because it's going to help me, especially some of these columns can be 1.2 meter by 1.2 meter. And when the moment you have 1.2 by 1.2 sections, like if I share the screen, I'm having 1.2 meter by 1.2 columns. So here 1.2 is somewhere here. Here you can see the maximum cement content has to be 300. Maximum cement content has to be 300, right? If I want to, because I'm having large columns, so I have to be concerned about it. So I can use 40 megapascal concrete with 30. So I'll use maximum cement kit is 300 cement, and I'll use something like 120 fly ash. Because I want 40 megapascal, I like to see that the cementitious content will be more than 40, more than 400. So I'm using 120 fly ash. If you look at the ratio, 120 divided by 400, what is the ratio? 120 divided by 420. 120 divided by 420 is 18%. So it's okay. Right? So it's 18%. So I have about 18%. So I can even use 150 here. Right? So 150 fly ash will give you 450. 150 divided by 450. So I'm getting 150 divided by 450. 33% is too much. So if I have 120 divided by 420, what is the answer? I think I got it. 28%. So that means I cannot use 120. I have to use about 100 fly ash and 300 cement. 400, right? 400. Now I cannot increase the cement content. Now you can see the problem. Sorry, I'll stop here. Right. You know the problem. I can't use too much cement. The maximum cement is 300. I want to get 40 megapascal. So I'm going to say wet density is 2470. Lot of fly ash there. I say I'm going to use 130 by using a high grade superplaster. So the normal superplaster will allow you 160, 150, 160 range. High grade superplaster will allow you 120 to 130. Now I'm going to look at numbers. 2470 minus 400 minus 130. Now this is in a column. So this is in a column. I have to pump. So I'm going to use Y over X ratio as 1.5. So I like to get high strength also. So I don't like to use too much sand. I like little less sand, but at the same time I'm little restricted. So I'll divide this by 2.55. So I need 2470 minus 400 minus 130. 1940. Okay. Divided by 2.5. 760. And multiplied by 1.55. 1180. So what can I say about the cost? Cost is 300 multiplied by 40 plus 100 multiplied by 15 plus 760 multiplied by 550 plus I'll use 600 of 500 of half inch, 680 of 3/4, 500 multiplied by 250 plus 680 multiplied by 225. That's the cost. Plus 1950. 22,500. So what is the cost difference between 40 megapascal, 30 megapascal and 40 megapascal concrete? It has to be less than 2,000 rupees. Can you see the ability to do calculations like this is very vital? Bashita, what do you think? It's a vital skill that an engineer should have so that he can start controlling the cost. Controlling the cost of the project is very important these days because we are in a crisis.
So I have a question. May I ask?
Yes.
So in this 40 megapascal,
who are you?
Yeah, in this 40 megapascal simultaneous products is 400, but you have used 100 for the fly ash, then it's exceeding the 15% to 25%.
No,
So
no, no. The maximum is 25%. Without any fear, you can go for up to 25%.
So then
The
once we
ratio, without any fear, you go up to 25%. No need to worry about it.
So then, sir, the material safety factor gamma m would change in that partial
No,
safety.
Okay, that's a very good question. I'll give the answer. Don't worry. Right? Okay. That's a very good question. I'll give an answer. Okay. So basically the answer is, if you are using higher fly ash, do you have to you have to increase the factor of safety 1.5 for concrete strength. Is that right?
Yeah, that's a question, sir.
That's a question. A very good question. So I'll answer it. Now we look at, now let's say, what is the other alternative? Now, if you don't know anything about DEF in a column, what would you do? You want 40 megapascal concrete, you let's say cement, 400, sand, aggregate, water, 130, and aggregate is 1180, 760. Now, your question is, what is the difference between these two concretes? Okay, first difference. I'm going to share now. Share the screen. Look at this chart. So you are having 400 cement. That is 1, 2, 3. 1, 2, 3. Here. You don't know anything about DF. What is the size that you can cast? You have to cast the maximum size you can cast is about 400 millimeters. Is that clear? Without any risk of DEF, what is the maximum size you can cast? Can you see the chart? Maximum size is even less than this, less than 500. Now, what is the option you have? You are insisting that you want this cement. What are you going to do? You have to reduce the placing temperature by using flakeyards. So, you reduce the placing temperature by 6 degrees. You go up to 32, you go up to 26. 6 degree less. 6 degree less means you have to be somewhere here. So in that case, you can cast a section up to about 600 without worrying about DF. Is that clear? Just look at here. Something like 76 degrees will be here. And use the chart you are referring, so you can go up to about, if you reduce the placing temperature up to 26, you can go up to 600 section without any fear of DF. Is that clear? Even somebody else can answer. Is that clear?
Yes, sir.
If you are using 400 cement, the maximum size you can cast without any fear of DEF is around 400. But if you reduce the placing temperature up to 26 degrees, you can go up to about 600. But you can't go up to 1002 because there's a risk of DEF occurring, but generally it doesn't happen. But because columns are kept very dry. But you are risking the building because you don't have enough knowledge. So you have knowledge, you look at it and you decide, okay, I'm going to do some fly ash. And let's say you have decided to go for 350 or 15% of 400. What is the 15% of 400? 340. 340 cement. Is that right? Yes. 60 fly ash, 340 cement. What is 340 cement? This one. 1, 2, 3, 4. Okay, 340 cement, 350 cement. 1, 2, 3, 4. And you are reducing your placing temperature. Now you can see you can go up to 1500. So just by looking at this temperature, this chart, you can say at which temperature you have to place the concrete, where the moment you know the cement content. Now, can you understand how to use this chart?
Yes, I understood.
The moment you know the cement content, the size of the member, you can either decide the placing temperature, or when you know the placing temperature, you can decide the size of the member. Because this chart is for 32 placing, but if you reduce the placing temperature by adding water to the aggregate heap the previous day, and then using 40% flaky ice, what can you do? You can easily reduce the placing temperature to about 26 degrees. But let's say you don't have this knowledge. Just allow the concrete to go on. What will happen? There's a risk of getting DF. Is that clear, Vashita?
Yes, sir, clear.
Right? So you can see this is a very valuable chart for the design engineer. So when he selects, he will not blindly select the cement content, he will not blindly select the grade of concrete, he will be fully aware of the difficulties of the construction contractor. He will be fully aware of the difficulties of the contractor, and he will address all those difficulties the time that he's designing. And that's the kind of sophisticated designs that you should produce as Sri Lankans. Then only you can capture the other markets. Is that clear?
Yes, sir.
Even for beginners, this is applicable. No? Even for beginners, this is applicable. Right, so I'll stop here. Now what will happen to the cost? Now cost will be very higher, much higher, very much higher. What is the cost? Cost will be 400 multiplied by 40 plus 760 multiplied by 550 plus 1180 multiplied by 2.25 plus 1950. 25,000. Okay, now we have two mixers. One costing 25,000, the other one costing 22,500. Now you use it. What will happen? The strength development curve of this mix B, this mix A, the earlier mix, where I use 100 fly ash. Mix B, it will generate a lot of heat, harden like hell. After about 5 days, you find now it has reached the full strength. But now it is going up very slowly, because after about 2 weeks, all tricalcium silicate reactions are over. So now it's going up very slowly. Now this one, that is mix B. Mix A is much slower. It goes like this. But before 28 days, it also goes above the requirement. So what are you looking for? In your design, you have said that I am looking for 40 megapascal in 28 days. So both mixers are achieving it. So what can you say about gamma M? Same. No change. Have I answered your question? The engineer who asked the question earlier, have I answered your question?
Yes, sir.
Yeah. So that's how you have to think. You know, you have to be vigilant and you have to think rationally. And you can do wonders with concrete technology. And you have to always look for the cost. Because we are substituting fly ash for cement, where fly ash costs only 15 rupees, whereas cement costs 40 rupees. And the other important point is, we have to be concerned about the target. So we set a target, 28 days, I like 40. So whether you achieve it in 6 days or 8 days or 10 days or 15 days, it doesn't matter. Then what matters? What matters is, have you cured it? Because for this one, curing is very important. This one, curing is less important, but the durability of this concrete will be lesser. Why? Fly ash will give chloride resistance, fly ash will give sulfate resistance, fly ash will also give a dense crust or dense cover zone. So which is better then? B is better. On paper, on the first glance, A looks better, but when you look at the desirable properties and the long-term properties, and also the ability for this to go beyond 40 is a particular advantage. Why? Let's say after 2 years, this has become 50 megapascal concrete. So what can you say about the 50 megapascal? It has become 50 megapascal concrete. And what is the elastic modulus? 35. And you, in the earlier one, you had only 40 megapascal concrete. 35, 40, 37, let's say 37, 33. So elastic modulus would be around 33, whereas the other concrete, the type B concrete, might one day achieve 35 and it might even become 36. By the time you are selling your apartments, the building has become much stronger than that you ever thought originally. And what is the time you need the very good dynamic behavior with respect to wind-induced accelerations. At the beginning of the project, by the time you sell your apartments, if the building is stiffer, it will have a lesser wind-induced acceleration, and you'll find now, people are happier because your calculation was more based on 1 year return period. Now suddenly you find now you are even satisfying the 5-year return period on the wind-induced acceleration limits. And you'll find you have a much superior product. And that product improvement has come from the concrete technology that you use, not by the design. Is that clear?
Yes, sir.
Right, good. So I think we are coming closer to the time. So what is the reason to limit the concrete grade difference to NRI? Okay. So basically, that's again a good question. So when you are doing this concrete, now we have a beam zone. The column is going above, right? So this is the beam. So beam is 30 megapascal. Column is 40 megapascal. But in this zone, you have a lot of reinforcement. So because of this huge amount of reinforcement, there's a huge amount of confinement. So even 30 megapascal concrete can easily transfer the load, that is the stress that is induced in a 40 megapascal concrete. So that's the reason. So even in a raft foundation, you have a lot of reinforcement in these directions. So you have 40 megapascal here. Here you have 30 megapascal. It doesn't matter because because all these reinforcement can do the dispersion into the concrete. And anyway, 40 megapascal concrete, the working stress will be 0.4 times 40. So it will be 16. And for 30 megapascal concrete, again will be 0.4 into 30, 12. So you can see, although we are having a difference of 10, within the structure the difference is only 4 at the working under the working stresses. So this difference of 4 can be easily accommodated by the reinforcement. So that's why the beams can be 30, columns can be 40. You don't have to do anything, but it is limited to 10. Otherwise, this difference will become too much for reinforcement to handle. So that's why the maximum difference allowed is 10. Is that clear? Have I answered the question?
I have another few small question.
Yeah.
So as you said, the maximum of 25% of fly ash can be used. So
Yeah.
do we have to add any alkaline activator solution if we use 25%
No. Up to 25% fly ash, you are free to do anything provided fly ash is type F and the carbon impurities are low. So you have to get the fly ash from which has passed the tests. So if you ask a cement manufacturer, they buy only the fly ash that pass the carbon test. So if there's too much carbon, then it's an impurity. So you have to actually get the specification for class F fly ash. Check whether the product that you buy satisfy that. But the moment that many construction companies are buying fly ash, it will become readily available, high quality fly ash. Is that clear?
Yeah, thank you, sir.
Yeah. But if you are going beyond 25, you have to be careful. You have to do tests. Because in one point in Sri Lanka, I think ICT tower, ICC did it. Mr. Engineer Samita Jayakodi did most of the concrete technology part. I think they went up to about 35% or 40% fly ash. But it has to be done very carefully. Purely for the temperature control. But I think that probably the design engineer asked for 40 megapascal, which is not a good thing. And anyway, in Sri Lanka, pile rafts are not necessary. Pile rafts cannot work in Sri Lanka because Sri Lanka is having bed. Pile rafts work only with friction piles, not with end bearing piles. So it's a wrong concept. So any engineer thinking of doing a pile raft, you have to be very careful in Sri Lanka, because if you are doing a pile raft, then you can do pile rafts only in the areas having very good laterite soil, where the bedrock is deep, where you are going to stop the piles in the laterite soil as friction piles. Then you can go for a pile. But otherwise, if you are having end bearing piles, going for a pile raft is wrong. So that's why I say, I checked and certified Altea. I could not change the design. But today, if I am doing the same design, the weight of Altea will be 60 to 70% of the actual weight that it is carrying today. Because there are so many ways of actually optimizing the design that we have developed in recent times. So any structure, any building that you going to get, I can show you how to reduce the structural cost by 40% by reducing the weight of the building and optimizing the foundation. So there are many things that you can do. And these days we are doing a project where, what is the general capacity of 1,200 pile? 6,000 kilonewtons. What is the general capacity of 1,500 pile? 10,500 kilonewtons. But in this particular project, our 1,200 piles of 40 megapascal will carry 11,000 kilonewtons, nearly twice, and our 1,500 millimeter piles will carry 17,000 kilonewtons, all with 40 megapascal concrete for the pile sheet, with 0.7% maximum reinforcement in the pile. So there are so many things you can do, provided you know the fundamentals. So basically, we have knocked off about 50% of the piles in that project by going for high capacity piles, heavily loaded. So there are so many things I can teach you. I'll continue to tell many things, but it's very good that you are asking questions. The moment you ask questions, you can see so many things that I never thought of explaining came out. So your active participation is fully appreciated. So any other questions? So I can stop here. The next day we'll continue, because we have plenty of time. Even if you have 30 lectures in this series, it doesn't matter. So we'll continue gradually. Right.
So there are some questions in the chat box as well.
Can you tell me what are the questions?
Yeah, sure. At the very beginning of the lecture, Engineer PSN Silla asked, is it worth to study about Tarantula curve and concrete mix design?
No. What I say is, there are so many, huge amount of research has gone into concrete mix design, because nobody could get it right. So because of that, I developed a simple method, which is purely based on logic. Now, that's why I showed you how I manipulate the numbers. So I know only two things. One is cement is the friend. What is the enemy? So I manipulate the enemy. The moment I manipulate the enemy, and make it small as possible, I can bring the cement content down in a drastic manner. Have you got the point? Then what I do is, I will cast a lot of cubes using the mixers I have selected, and I will develop our own strength development curve. We cast a lot of cubes and make the strength development curve, and use that data as our own data for quality assurance and quality control. That's the way I look at it. Is it okay?
Yes, sir. Then
What is the next question? So our engineers are very reluctant to go ahead with the strength development curve. So they think it's a waste of money. No, it's not a waste of money. It's a real asset. It's a knowledge base, your database. And then even a consultant cannot say, I have read this literature and that literature. Why? Because the contractor has a curve that he has developed with his own testing. And if the consultant challenges, he can cast few more cubes and show that that curve also coincides with the curve he's having. So the moment it's verified for about 1 month, the consultant will have to back down. So as contractors, you should know how to handle the consultants. Because in Sri Lanka, what happens is consultants simply have a huge authority, because contractors are not knowledgeable. But when the contractors are highly knowledgeable, like in Australia, they simply challenge the engineers. If your design is not cutting edge design, these builders will laugh at you, and they say, you take your bloody useless design, I'll get it done by another guy who is doing cutting edge design. So that's how they do it. They simply say, this is over design, and I'm not going to listen to you. So in Sri Lanka, it's other way, where the consultants have a huge authority, whereas in actual practice, like in other countries, you don't have, the consultant has to be very knowledgeable, because contractors are extremely knowledgeable. In Sri Lanka, contractors are not knowledgeable. That's why the consultants can have huge authority. Any other question, Rashika?
Yes, sir. Then engineer Ekanayak asks, how about the steel structure with this hollow pole?
What is that? Steel? That hollow pole? That is pre-stressed concrete. It's not reinforced concrete. So that's why they wanted 65 megapascal in 24 hours to debond it. Do the debonding. Right?
Okay.
So it's a pre-stressed concrete pole. So it's a hugely stressed curve. So it's a stress pole. So it's very strong. You would have seen this used by Sri Lanka Telecom. Now, there's one engineer, Dr. Nadira Gunatilaka. He is the one who initiated this, and now it's widely used here by Sri Lanka Telecom. He was at Sri Lanka Telecom before he joined the Open University. So Dr. Nadira did his PhD on towers at Moratuwa, but when he was after completing his PhD, he joined Open University. But before that, he was at SLT and he did a lot of innovative work. Any other question?
Yes, then engineer Sajeev Kant asks, for mixed proportion calculations, which strength to use, cube strength or cylindrical strength?
No, I'm using cylinder cube strength, no cylinder strength, because the moment you know the cylinder strength, you know the cube strength, because this table is available. So the moment you know the cube strength, you know the cylinder strength. So all these construction technology is based on cube strength. Why? The cylinder strength is readily available. So whatever the Eurocode design you can for construction technology, because we have developed the construction technology when the cube was available. So now I don't want to change it. I can change it, but I don't have to do that. I can still go with cube strength, because Eurocode supports cube and cylinder both. But if you are designing for Eurocode, it's a cylinder. But for construction technology, they have not said anything. So you can use either cube or cylinder. But in this particular case, I am using cube strength. Okay, any other question?
Okay, sir. Finally, Engineer Ekanayak asked, any issue recorded for PS design with fly ash shedding?
Again, repeat the question.
Any
Slowly.
issue recorded for PS design with fly ash shedding?
So British Standard Designs. You are saying
Sorry?
BS designs or what is that? Pre-stress concrete.
PS, yeah, pre-stress design, yeah.
No. Pre-stress concrete, you have no problem. But you know, in pre-stress concrete, why do you need fly ash? You don't need it. Why? In pre-stress concrete, the section should be as small as possible, as thin as possible. If the section is thin, if you want workability, you can use about 10% fly ash. But otherwise, to cast pre-stress concrete sections, you don't need fly ash. Fly ash is needed to avoid DF. So if the sections are thin, pre-stress concrete, you can't use massive sections, then it's not economical. So in pre-stress concrete, what is economical is sections as thin as possible. Is that clear?
Yes, sir.
So in pre-stress concrete, there's no need to use fly ash, but sometimes for workability, because fly ash can give a huge improvement to workability. So because of that reason, sometimes the engineers say, okay, I'd like to use 10 or 15% fly ash. Because in pre-stress concrete, what matters is what is most important is the early strength. So early strength, if you know high early strength, don't use fly ash. But if you have run the risk of DF, then use fly ash. Pre-stress concrete are thin sections, whereas reinforced concrete are massive sections. So in reinforced concrete construction, you can use fly ash, but even for pre-stress concrete, you can use fly ash to reduce the cost of construction. Because it gives a very nice finish with very good, cover zone that is resistant to chlorides and sulfate. So in highway bridges, it's worth using 15% fly ash. Even with pre-stress concrete members, because you might be using various chemicals on the road. And vehicles also drop various chemicals, so they might come and they might be even in the coastal zone, there may be chloride attacks. So all those can be very well controlled if you are using 15% fly ash in pre-stress concrete members. So the reason for using fly ash in pre-stress concrete is actually it's detrimental, but if you are interested in reducing the chloride attack, then using 15% fly ash is highly recommended. So for each thing, there is a different reason. Any other question, Bashi?
That's all, sir.
That's all.
Yes,
shall we wind up then?
Yes, sir. Let me deliver the official
what are that?
Yeah.
Closure.
Yeah.
Okay.
I am pleased to deliver this out of thanks for the second session of the webinar series on structural design of reinforced concrete members subjected to flexure according to Eurocode, conducted by Professor Sanjay Singh. On behalf of the organizing committee, I would like to express our heartfelt gratitude to Professor Sanjay Singh for his insightful and informative presentation. The webinar series has been a great success, and we have received numerous positive feedback from participants. This would not have been possible without the support of CEC Chairman, Engineer Mangal Silla, the IECL Secretariat, the Publicity Department, and the IT team. We would like to thank them for their dedication and hard work in making this event a success. We would also like to express our appreciation to all the participants for their active participation and insightful questions. Your enthusiasm and engagement have made this webinar series a valuable learning experience for all. Finally, we would like to inform you that the next session of the webinar series will be on the 13th of December. We hope to see you all there. Thank you. Thank you, sir.
Yeah, Bashito Banduka. Bashita, now, so next week, because I thought of touching on the design, but because a lot of questions were there and so on. So next time also we are starting, we'll be starting on that, design aspect. But before I start on the design aspect, I will tell you a few stories that will give some insight for those who are practicing as consultants. Is it okay?
Yes, sure.
Yeah, okay. So next time, so I will spend little time on telling few stories that happen in Sri Lanka. Not to insult any engineer, but very good for us to know, because sometimes we make mistakes and then only we learn from the mistakes. So it's good to know that what happened in various large projects in Sri Lanka and how we came out of the mess. So that will give you a lot of insight to the consultants, giving them the idea what is the time they have to be extremely strict and what are the times that they can be lenient. So that way, you can avoid disasters in construction. But I'm sure you would have learned that construction is not just carrying out the duties expected by the consultant. It is doing it with the understanding so that you can start challenging the consultant. So that's the whole idea, is to give you that in-depth knowledge so that you can be, we can develop together. Consultant and contractors all can together develop our construction industry to a higher level so that it will not go into a mess like that happened in 2020. Thank you.
Thank you, sir. Thank you very much. Good night.
Good night.